Hi friends, hope you are doing well. Welcome to my channel. So today we are going to discuss Aerodynamics lecture 4, and today I'm going to talk about flow separation. I'm Dr. Ranjan Ganguly. Now we are going to see that flow separation has an important effect on things such as the pressure drag and the skin friction drag. And this is very important because in most aerodynamic applications we need to predict the drag properly, and therefore we need to have a good physical understanding about what is the source of the drag on a typical airfoil section or even on a typical blunt body. So today we are going to consider a case where an airfoil is placed at a high angle of attack, and the adverse pressure gradient in this case becomes severe and dp by dx becomes large. So what happens in this case is that the real flow tends to separate from the surface. Now this will become clear when you look at the figure here with the airfoil section, and you can clearly see that the flow here tends to separate. So essentially there are these fluid particles which are going through a reversal in terms of their velocity. So this is essentially what is the flow separation, and this can be seen in wind tunnel experiments and so on. So what actually happens to the pressure distribution on the top surface when there is separated flow? So if we look at the pressure distribution, we see that if we did not have any flow separation, the dotted line would be the situation here. So there would be a very large pressure here or a large negative pressure here, and then there would be a change here, and you would go to some point here which is higher than the 0 point. But what happens in the case of the flow separation is that the pressure comes down, then it goes like this. So essentially this is real flow. This does not recover to free stream, so you can see it stays somewhere here. So this is the actual nature of the flow which we get because of the flow separation. Now, what are the consequences of separated flow? We can see the first consequences is going to be a drastic reduction of lift, and this is sometimes known as a stall phenomena. We're going to discuss that in more detail later. Now, what happens as far as the aerodynamic lift is concerned, that it's derived from the net component of a pressure distribution in the vertical direction, and this component is going to get reduced. Now, high lift is obtained when the pressure on the bottom surface is large and that on the top surface is small. So that's the way pressure is essentially generated on an airfoil section. Now, separation does not change the bottom surface pressure distribution, so that's something to remember. It's only going to change the top surface pressure distribution. So if we now look at the figure of the two cases, so the red line here is the attached flow situation and the black line here is the separated flow situation. So like I mentioned before, the pressure distribution on the bottom of the airfoil remains the same, but on the top of the airfoil the pressure distribution changes. So if we now look at how the lift is coming, the lift is going to be greater as far as the attached flow is concerned because the pressure on the top surface is less. So you can see in the red line the pressure on the top surface is less, and so there is a greater lift here which is going to fall when we have the separated flow pressure distribution. But we will also see that as far as the drag is concerned, the separated flow drag is higher because the forward component of pressure which is coming from the trailing edge is now less. So in the case of attached flow, you can see here in the red lines and so on that there is a forward component acting here for the pressure, and so that's going to be in the reverse direction of the drag. So the attached flow situation is going to have less drag, it's going to have more lift. So both these are of course beneficial from the aerodynamic and practical point of view, but the separated flow is going to have lower lift and it's going to have more drag. So again, both these are things which you do not want in general. So now let's discuss some of the things which are happening here in more detail. So we can see that flow separates because of the adverse pressure gradient, which basically means that dP by dx is positive. Now, when this happens that dP by dx is positive, the fluid particles move along the streamline must work their way uphill against an increasing pressure. So you can think of this increasing pressure like a hill, and so the fluid particle is trying to climb up this hill, and so therefore this pressure distribution is proving to be too onerous for the fluid particle, and it's going to slow down, maybe come to a zero velocity, and then maybe even go back. So the fluid element therefore slow down when confronted with this adverse pressure gradient, and the fluid which are outside the boundary layer have high velocity. Remember, they are pretty far away from the surface, so at the surface the fluid elements have zero velocity. So what happens is that they continue to move downstream. They have enough velocity, they do not care about the slowing down. But the fluid elements which are in the boundary layer, they are going to have lower velocity. Remember the profile of the fluid in the boundary layer, and they cannot handle this growing pressure which they are facing. So what happens is they are going to come to a stop and they reverse their flow direction. So this is physically how you can think about the flow separation taking place, is this reversal of flow direction, and this causes the flow to separate from the surface. So essentially this action all happens inside the boundary layer because the boundary layer fluid particles are moving slowly compared to what's going out on the free stream. Now let's look at the different way this happens in the turbulent and the laminar boundary layer. Now remember that the turbulent boundary layers have fuller velocity profiles. Okay. So what happens is that if you are at a given distance from the surface, the velocity of a fluid element in the turbulent boundary layer is higher than for a laminar boundary layer. Okay, so the turbulent boundary layer has more Ke near the surface, and therefore the flow is less inclined to separate. So this is very interesting that in the turbulent boundary layer case, because the fluid particles have higher velocities compared to laminar boundary layer case, the flow is actually less inclined to separate. So we can say that the turbulent boundary layer is more robust to flow separation. Now, if we look at the laminar boundary layer, here the flow separation takes place more easily than turbulent boundary layer. And to prevent flow separation, we would always like to have a turbulent boundary layer. So this is an interesting and somewhat counterintuitive thing which comes out of this flow velocity situation. Now, let's look at the sources of drag. Till now, we have realized that friction is the key cause of drag, and friction is ubiquitous as far as the real world is concerned. So the presence of friction in the flow produces two sources of drag. There is skin friction drag due to shear stresses at the wall, and there is pressure drag due to flow separation. This is also sometimes known as form drag. So if we want to minimize skin friction drag, then we need to maintain a laminar boundary layer, because do remember that skin friction drag is coming from the tau value, and that is coming from the dv by dy at the surface. So essentially at y is equal to 0. So essentially skin friction drag will always be minimized by maintaining a laminar boundary layer. But pressure drag is reduced by maintaining a turbulent boundary layer or establishing a turbulent boundary layer. So essentially there are two different requirements here, and this is a typical situation which happens in many engineering problem, that if you want to actually reduce both these types of drag, you need to find some compromise solution which is there. So that will be required if you are trying to design any airfoil or any cross section which is going to produce lift and going to have a lower drag situation. Now, if you are dealing with a blunt body such as a cylinder, the drag is mostly pressure drag because there is flow separation, and so turbulent boundary layers are going to be preferable. So this is something which you get from blunt body situations. However, if you have a slender body such as an airfoil, the drag is mostly skin friction drag. So in this case, laminar boundary layer is preferable. So essentially, this gives you good insight in terms of design. Whenever you are designing something such as an airfoil, a slender body, you essentially want mostly low skin friction drag because most of the drag is coming from skin friction, and therefore laminar boundary layer is preferable. So the total drag due to all these phenomena is known as viscous drag, or which is taking place due to viscous phenomena is known as profile drag, because it is dependent on the profile of the body. So very often the profile of the body itself can be optimized to bring down the total drag of the flight vehicle, and that is a subject for many design studies. So today that was the lecture as far as drag is concerned. You clearly saw that the drag is basically coming from pressure drag and skin friction drag, and these have different impact in terms of turbulent boundary layer or laminar boundary layer being there. So again, there is a trade-off here which is involved in terms of what is the particular vehicle or system you are trying to design, whether it is more of a blunt body, whether it is more of a slender body, and so on. So that was the video for today, and I will see you in a video sometime soon. See you then.